A design rainfall is an input, is what we use as input in a hydrologic model, which is a mathematical equation that will transform a rainfall event into a discharge amount. So this design rainfall is what goes as input in this model. And this design rainfall is used to estimate the design flood. Okay, and that design flood is what we need to define the dimensions of our engineering infrastructure. Design rainfalls, they come from statistical analysis. So it's what we call a frequency analysis of long-term historical data. Okay, so we have a long-term, let's say 30 years of rainfall records. And then we analyze the probability of a certain amount of a certain intensity of rainfall occurring in a given year. Okay, so we determine how probable it is to experience that particular amount of rainfall in a given year. Okay, so this is what we call frequency analysis. The rainfall data comes from rain gauges or pluviographs. The rain gauges, they usually give you a rainfall amount after a given period of time, for example, one amount per day, one reading per day, and the pluviographs, they give us a variation of rainfall over time. So it's more like an instantaneous reading of rainfall. There are many more gauges, rainfall gauges, than pluviographs in our rainfall data system. So design rainfalls are probabilistic in nature because they are associated to the likelihood of occurring in a given place. Okay, and we usually associate a annual exceedance probability to each rainfall intensity, which means the probability of that particular intensity being equaled or exceeded in a given year. So design rainfalls are therefore not real. Okay, they're not observed rainfall events, but rather they came from a frequency analysis of observed rainfall events. We usually associate three things with design rainfalls. We build this relationship between three characteristics of a design rainfall, which is the intensity, the duration, and the frequency of occurrence. Low frequency or low probability design rainfalls, they are high in intensity, okay? And they're usually used in the design of large and important water infrastructure, including reservoir spillways. Okay, so a low frequency rainfall event is one that is very rare. Okay, so it's a very high intensity. A high frequency or a high probability rainfall event is low in intensity, so it's a very weak rainfall event. And high frequency rainfall events, they are rarely used as design rainfall because design rainfalls are usually associated with lower probability, okay, of occurrence. Now we will be discussing various methods to estimate design floods from design rainfalls, okay, and here I'm going to list the 4 methods that we'll be looking at in this course. The first one is the rational formula. Okay, it's a very simple method, a very simple mathematical formula that will use a design rainfall as input together with some characteristics of the catchment, some simplified characteristics, and it will result in a peak discharge. Okay, so the rainfall method assumes that we have a rainfall event of duration d and constant intensity. Okay, so the intensity doesn't change over time, and that that rainfall event will generate a peak discharge in a catchment. Okay, we don't use the rational method to estimate the hydrograph because the hydrograph is considered as a triangle, which is not realistic. So we don't use this triangle to estimate the volume of the runoff, even though we could use as an approximation, but the actual use of the rational method is to find the peak discharge. Okay, it's the simplest method available and still widely used in some countries, including Australia. Another popular approach is the unit hydrograph method. Okay, so in this method, we use a design rainfall, and we use the hydrograph method, which we'll be discussing in one of the following weeks. But we use the method to generate a proper hydrograph, okay, which represents the response of the catchment to that rainfall event. From that hydrograph, we can derive the volume, we can derive the peak discharge, and the discharge over time. Okay. So this is both the rational formula and the unit hydrograph method. They are event-based simulation. What does that mean? It means that we use one single rainfall event as input and we have one single hydrograph as output. Another method to find hydrographs for use in our urban engineering design projects as design flood is the runoff routing methods or rainfall runoff routing methods. These methods, they involve transforming the runoff into discharge at various points of the catchment, not only at the outlet. And they use a flood routing procedures to find hydrographs at these different points of the catchment. Because of the complexity of the formulations used, we need to rely on computer programs which have this formulation all included in the coding. Okay, and some common examples of computer programs used in Australia are these ones. RORB is probably the most common one used in industry in Australia. So the runoff routing methods, they use either a rainfall event or continuous rainfall records as input, and they produce, if we have a single rainfall event as input, the output is a single hydrograph. If we have continuous readings, continuous records of rainfall, let's say a time series of rainfall, for example, day after day, one rainfall per day, then the output of the model will be a time series of the hydrograph. A time series of hydrographs is like a combination of various hydrographs in which we have various rainfall events and the corresponding response of the catchment to those series of rainfall events. Much more complex methods, and we're not going to be looking at rainfall runoff routing methods in this course. So I mentioned event-based and continuous simulation. Let's have a look at the differences between these two sorts of simulations or two sorts of modeling. In event-based modeling, we transform a single rainfall event, which is a rainfall depth of given duration, into one flood hydrograph, or a peak discharge value in the case of the rational method, in which we cannot use the hydrograph because the hydrograph is that triangle, which is not a realistic hydrograph. So rational method and unit hydrograph are examples of methods that are event-based. So input is a single observed rainfall event, or it could be a single hypothetical design rainfall, okay? So one event doesn't necessarily mean it's a design rainfall. As a single rainfall event could be an observed rainfall event. For example, if today we had 100 millimeters of rainfall, during a period of 5 hours, we can simulate, we can use that as input and see what the resulting peak discharge or the resulting hydrograph is. But that rainfall event is not necessarily a design rainfall, okay, because it's an actual rainfall event that we actually experienced. And the hypothetical design rainfall is the one that I mentioned, which is derived from an analysis of frequency of long-term data of rainfall observations. And the output of event-based methods is one single hydrograph representing the response of the catchment to that particular rainfall event. Or the peak discharge related to the simulated rainfall event, which is the case of the rational methods. Okay. Continuous simulation is the use of a time series of rainfall. For example, here on the top graph, we have a time series of rainfall events, of rainfall amounts. And as a response to that time series, we have a time series of discharges. So we can see that this time series is made up of various hydrographs. Okay, and so this is called continuous simulation. We can use this as in our designs. However, we need to do some post-processing with the data. We need to do a frequency analysis of this data in order to find the required design rainfall, design flood. So continuous simulation could also be understood as the production of data that would have been recorded at a location if a gauge were present at that location. Okay, so it's like a time series, a time series of discharges in a catchment, which would be the same as the ones recorded by a gauge if we had a gauge installed and operating in the catchment. So estimation of design flood using the continuous simulation requires the undertaking of subsequent statistical analysis, which is called flood frequency analysis, using the discharge time series then generated by the model. So we need to use this time series and apply a flood and use a flood frequency analysis to find the required design flood. The input in continuous simulation is a time series of rainfall and also evaporation, because evaporation is an output of the catchment. And the output is a discharge time series, that is various hydrographs. Flood frequency analysis is when we have catchments with discharge gauges recording flood levels or discharges, okay? Then we analyze that time series of observations and we apply or we use a flood frequency analysis method to estimate the probability of the floods and thus to find the design floods, okay? It's very rare, this method, because usually gauges, they are installed in large catchments and they represent the discharge of that immense region. And when we work with design, urban drainage design in particular, we are looking at very small catchments, and we cannot use the readings, the observations from the big catchment. We cannot use those times that time series for a smaller catchment. Okay, there is something called regionalization, which is when we transfer the discharges observed, the observed discharges from a large catchment to another catchment with using some parameters to correlate the two catchments. Then we can sometimes transfer those readings to a smaller catchment using some parameters to make this adjustment. Okay, so this is called regionalization. We're not going to be looking at regionalization in this course, but this is possible, and it's very important that you know and you're aware of this method as well. So flood frequency analysis is something that you can do if you have a long time series of flood observations, and using that series you will, for example, if this is the series of flood of discharge in your river, then you will apply some sort of frequency analysis method. For example, you can rank the floods from highest to smaller, and you can associate to each discharge, you can associate a certain probability, okay? So this is a flood frequency analysis.